Hello students, good morning. Welcome all of you once again. So today we will begin with our module 2, in which we will discuss some important terms like degree of freedom, constraints and generalized coordinates. These are the three important terms to be explained and discussed in detail. Okay. So let us begin with first the degree of freedom. So before going to discuss degree of freedom, let us have some idea about what is a particle. In fact, the concept of particle, we very frequently use this term, particle. Uh, Formally, a particle is defined as an object of insignificant size. So you see, examples are given here, interesting examples: an electron, a tennis ball, or a planet. So you may wonder what is the comparison, the spirit of comparison of electron, tennis ball, and planet. So keep in mind that this depends on the situation. Okay, for a particular situation, electron may be counted as a particle. For another situation, tennis ball may be counted as particle, and for another situation, any planet may be counted as a particle. So that depends on the condition or the relevance or which situation you are discussing. Okay, so that is why we say that validity of the statement depends on the context. So that is important. For example, you can count Earth as a particle when you calculate or describe the orbit around the Sun. So in this case, you see Earth is a particle. Or if you discuss the motion of the Earth with respect to the solar system, or you discuss Sun with respect to a galaxy, or in the universe, if you count the universe as a ball, then Sun is simply a dimensionless particle, a point. Even though Sun is enormously large, but in this particular context, Sun is simply a particle. So the sense of saying particle depends on the situation. And now you see, Earth can be even considered as a big object, an extended object, when you talk about the spin of Earth. Okay, the axial motion of the Earth. Or when you discuss the motion of a aeroplane, okay, aeroplane or a helicopter or a train, you can count Earth as an extended object. In that case, we have to count Earth as a big object. In that case, we don't say that Earth is a particle. Okay, so that is the meaning of the title particle. So it depends on in which context you are discussing a particular entity. In that context, even electron, you can talk whenever you talk about an electron and its spin, you take it as a entity, a real entity with some dimension. And proton, you can take it as an entity with some definite size. When you discuss about nucleons and nucleon forces, you have to count it as a sizable object. So where we don't count simply as a particle of dimensionless size, it has a dimension, it has a size, and many other parameters of these particles are important. Its spin is important, its charge is important, spin angular momentum. Okay, and many charges. Okay, charge is its quantization. In that case, many other microscopic quantum characteristics of these particles are important. So this way, if the particle context is a relative term, a relative idea, it depends on the situation. So hope the idea is clear now. Now let us describe another term that is called degrees of freedom. Degrees of freedom is actually, in fact, a number. How many? Okay, degrees. How many degrees of freedom? It in fact shows the variables or coordinates required to describe the motion of a particle, motion of a body, or motion of a system of particles like that. Okay, briefly, we can understand that it is the variables required to describe the motion. In physics, usually we need variables to describe motion. Whenever you describe motion, we specify its position. We may specify its position at different time instant. We may specify its momentum, velocity, angular momentum, energy. Okay, different parameters are there. So we can specify them. So these are all actually variables. Okay, depending on the condition, context, these all can be variables. So in fact, degrees of freedom is nothing but the variables, minimum variables required, coordinates required to describe the motion of a dynamic system. Okay, so let us see. You can describe it like this. It is a minimum number of independent variables required to specify the position of a dynamical system consisting of one or more particles. It can be a one particle system, it can be two particle system, or it can be a n particle system. Okay. You can generalize to any extent. For example, an example is given here for describing the motion of a free particle in 3D space. So the most simplest case, in a 3D space, we require three coordinates x, y, z. Okay, so then we say what? The number of degrees of freedom of the particles. So it is a fact that in a 3D space, if there is a free particle with no restriction upon it, it is freely to move in any direction. Okay, so then we need x, y, z coordinate variables to describe its motion. So then we say its degrees of freedom is 3. Okay, so the idea is clear. Numbers, it's a number actually. How many? This is answer the question, how many variables? So how many is very important. How many numbers? Come to another situation. So we have a particle revolving in a circular path in a two-dimensional plane. Okay, we have a particle here moving in a circular path in a two-dimensional plane. So there are certain restrictions on the particle now. In the previous case, particles were moving randomly, and we need three coordinates. But here it is not a random motion. It is confined to move in a plane as well as along a circle. There are two restrictions on the particle. One is to move in a plane, not free to move in a 3D space, and secondly, confined or restricted to move in a circular path. So how we will discuss? In fact, if it is not restricted, it had 3 degrees of freedom, but here it is limited. So there are constraints. You can say these are all constraints actually. The limitations or certain restrictions imposed on the particle, we call it qualitative constraints. What are the constraints here? First constraint is it can move only in xy plane. So z is 0 is a constraint. Okay, you can write mathematically. Even though constraint we call qualitatively as a restriction or a limitation on a particle, but mathematically you can say, you can express it z is equal to 0 is the first constraint. What is second constraint? R is equal to a constant. Radius is a constant is another constraint. Or you can say x square plus y square is equal to a constant. That is also true. X square plus y square is equal to a constant. So there are two constraints. So you can see that from the diagram, you can express its position with respect to a simple angle theta and radius. Radius is constant. So at any time instant, its position can be represented with r and r cos theta or r sin theta like that. So only variable required is theta here. You can express x using r cos theta and y using r sin theta or vice versa. So theta is the one and only variable required to express its position. So we say that only theta is required, only one coordinate, one variable required. Say we say that the degree of freedom of the particle is 1. Degree of freedom of the particle is 1. Similarly, you see another dynamical system here. A particle is this is not a particle; it's a bead. Okay, bead just used in ornaments. A bead is taken to a small needle, and the bead is moving along the needle to and from motion. So in this case, again, you can see there are so many restrictions. It is restricted to move along a single direction. along a single axis. Also, you can say that you can represent its position with a single variable, say x. Okay, x is the only variable required to represent its motion. So we say that degree of freedom of this particle, a bead moving along a stick or moving along a pin or a wire, is 1. Degree of freedom of this bead moving along the wire is 1. Okay, so you got some physical intuition regarding the concept of degree of freedom. Okay, so we have a few more examples here. Now you have a two-particle system. Two-particle system. It is given shown here, and it is free to move in a 3D space. Okay, so there are two particles and 3D space. So for one particle, we need 3 degrees of freedom. So for a two-particle system, how many degrees of freedom will be there? There will be 6 degrees of freedom. Understand? 6 degrees of freedom. Okay, that is the case of a two-particle system. So if you come to an n-particle system now, an n-particle system, so you can say for single particle you have 3 degrees of freedom. So for n particle there will be 3n degrees of freedom. Okay, suppose the number of particles is 10. So the total degrees of freedom of the system will be 30. So that means 30 variables are required to express its configuration or to express its motion or state at any time. That's the meaning of this. Okay. So we generalized it. Okay. So we once again say that degrees of freedom is the minimum number of coordinates required to describe the configuration of a system or to specify the exact location of the object of the system. And it is important in describing a mechanical system that we will see in the due course of time. And we have already discussed this minimum number of independent variables. These are different definitions given by different authors. You can take any description and any definition provided that it carry or convey the meaning. Okay. And when we discussed degrees of freedom, we said that particles or bodies are restricted or there is some limitation imposed on this. These limitations are actually called constraints. Okay, the limitation is imposed on the motion of a particle or a system of particles is called constraint. When a particle is restricted to move in a plane, constraint is z is equal to 0. When a particle is constrained or restricted to move along a circular path, then we say radius is constant. That's a constraint. Understand? Example is given: electron moving in a circular path, or a small metal ball moving in a circular groove. That is an example. Another example is given: a pendulum oscillating in a plane. Okay, then length is a constant. So length is a constraint. You cannot vary the length. And plane of oscillation is a constraint because it can move only in the xy plane. So two constraints are there. For an oscillating pendulum, you can say two constraints are there. And suppose the pendulum bob is moving freely in space. Suppose bob is moving freely in space. There is 3 degrees of freedom. But when that same bob is suspended from a string and oscillated, two constraints are coming upon it or imposed upon it, so that now the degree of freedom reduces to 1. So 3 minus 2 equal to 1. Okay, so that is shown here. If you imagine that the bob is moving in a spherical polar coordinate system, then we need r, theta, phi. Okay, variables in the spherical polar coordinate system. But the moment you reduce restricted motion in a plane on a simple pendulum, you need only one variable to describe its motion. Only phi is needed. Azimuthal angle is required. Okay, phi will represent its position at any time. Okay, another example is given here. For a cylinder rolling down on an inclined plane, the normal reaction from the plane is constant. This is a constraint, normal reaction. So constraints depends on the mechanical system. constraint, not necessarily always position variables. Constraint can be of any type. Okay, sometimes momentum can be a constraint, sometimes force can be a constraint. Situation vary. Okay, so in fact we are more concerned with the force constraint. Different forces act as constraint. So using that concept, many mechanical systems can be understood, explained well. Okay, so constraint forces we will discuss very shortly. And constraints, now you can classify them into two categories. One is called holonomic constraints, one is called non-holonomic constraints. Okay, let us see what is the difference between these two. What is holonomic, what is non-holonomic. So okay, come to the first one, holonomic constraint. What is a holonomic constraint? So come to this example again. Here is a bead moving along a circular wire. There's a bead moving along a circular wire. Okay, it's the simplest example. Here you can see its radius is constant, as I already discussed with you. So when you write the constraint in mathematical form, what we write, the radius of the circular path is a constant, or x or r is equal to a constant. You can write r is equal to a constant. Okay, so where we used the equality sign, r is equal to a constant. So any constraint that you express in mathematical form, and if that contain an equality sign, then you can call it a holonomic constraint. Okay, you need an equation, you have a constraint. If you express a constraint in mathematical form, then if that mathematical form contains an equality sign, then we call that condition as a holonomic constraint. Example, one more example is given: a rigid body. Distance between any two, okay, in a rigid body, all the constant particles are fixed. So interparticle distances are constant. So it is an holonomic constraint, a simplest example of holonomic constraint. Ri minus Rj is equal to Ci, where C is a constant. Ri is the position vector of ith particle. Rj is the position vector of jth particle. So the distance between them is always constant. You can even write vector Ri minus vector Rj, no problem. And its magnitude you can take, and that magnitude is given by Cij. Okay, this is the most generalized form. So in a rigid body, the holonomic constraint is Ri minus Rj equal to Ci. But again, there is an equality sign. That means the example for holonomic constraints. Okay, so and in the case of a bead moving along a wire, you have written already R is equal to a constant, or R minus A is equal to 0. Or if you are writing in terms of Cartesian coordinates, you can write it as x square plus y square equals r square. Again, an equality sign comes. So these all are the examples for holonomic constraints. Okay, you can even consider gas particles in a chamber. Okay, suppose you imagine that gas particles put in a cubical box kind of like this. Then all sides are of equal length. So you can write side. Okay, side you represent as S equal to a constant. That is a constraint for it. S equal to constant. A few more examples are again here. As already we have discussed this one. For a particle moving on the surface of a sphere, if you take the particle moving on the surface of a sphere, okay, in that case what happens, it is confined to move on the sphere, okay. So in that case, the radius from the center is a constant. Imagine for example, an ant moving on the surface of a ball, and is restricted to move on along the plane. Okay, so it has degrees of freedom. How many degrees of freedom do have an ant? Of course, it may have 2 degrees of freedom, because its r is constant, theta and phi can vary. So we say that degree of freedom of an ant moving over a spherical ball is 2. Okay, so that means we need theta and phi to describe its motion. R is constant. Okay, so here you must note that we have to take care of certain important points while fixing degrees of freedom, while fixing the minimum number of coordinates, etc. That is given here. First thing, the number of degrees of freedom is independent of the choice of coordinate system. Okay, in the previous example you can see an ant moving over the surface of a sphere. You can represent even using ant's position using x, y, z. In a Cartesian coordinate, you can represent its motion. And even in a spherical polar coordinate system, you can represent its motion. But you see the most convenient one is a spherical polar coordinate system, so that you can cut down the number of coordinates. Because in XYZ system, you cannot eliminate any XYZ. But when you go for R theta phi, you can eliminate R. So it depends on the situation. Okay, and minimum number of degrees of freedom is independent of the coordinate system. Okay, even you can write x, y, z by fixing one of them. Okay, by fixing one of them. That way you can reduce any one of the variables. So that is also possible. For example, x square plus y square is equal to constant, or x square plus y square plus z square is equal to constant. So you get to one holonomic constraint: x square plus y square plus z square is equal to constant. Okay, so that one of your variable can be removed from the equation, isn't it? You have x square, y, z. So taking the x square plus y square plus z square is equal to a square relation, one of the variable can be removed. So you can write in terms of the remaining two variables. So that means the number of degrees of freedom is independent of the choice of coordinates, because in R theta phi you can remove R, only theta and phi is left. Similarly, x y z system you can remove any z, you can rewrite in terms of x and y. So again, minimum number of coordinates is x and y. So that is the meaning of this statement. Secondly, there are freedom for the choice of coordinate system. Okay, so that depends on you which one will be most suitable, whether it is spherical polar coordinate, whether it is cylindrical coordinates, or what is called or a Cartesian coordinates, or any other curvilinear coordinate system. That depends on the physical system which we are discussing. Always choose such a coordinate system in which the degree of freedom is minimum and the system can be well explained. Okay, so that is important. So by choosing minimum variables, you can solve the problem much easily. And the selection of coordinate system depends on the mechanical system under consideration. Okay, which one will be suitable? Because when you are discussing the motion of a fluid through a pipe, you may go for a cylindrical polar coordinate system. Understand? And when you discuss the motion of a satellite or a flight on the Earth, perhaps you can go with a spherical polar coordinate system. Understand? And when you discuss the motion of a particle in a rectangular box, you may perhaps go with a Cartesian coordinate system. So that depends on which system we are discussing, and appropriate selection can be done. Now we can make some generalization regarding a 3n particle system. Suppose there are k number of equations to describe constraints. Or imagine that there are k types of constraints on a system. Just like that in the pendulum we discussed two types of constraints. One is plane is fixed, secondly length is fixed. That is where k is equal to 2. And in general we assume that there are k constraints on an n particle system. K constraints. So what we can do? In fact, there are 3n variables needed to describe the system. But k number of coordinates you can remove because there are k constraints. So what is the number of variables remaining then? The degrees of freedom will be 3n minus k. So you can write the degrees of freedom of the system is 3n minus k. Understand? Degrees of freedom is, so the total variable, number of total variables required to describe the system satisfactorily reduced. Okay, satisfactorily we can describe the system with the 3n minus k variables. Okay, so n is equal to 3n minus k. So using this notation, you can calculate, you can compute the total degrees of freedom of any system in the world. Okay, provided that you know this relation, provided that you know how many dimensions required to express the system. First thing. Okay, whether it is a one-dimensional system, two-dimensional, or three-dimensional. Secondly, if you know the number of constraints acting on the system, two things need to be known. Then you can find the total degree of freedom of the system. Okay, this is again a count. Okay, numbers, and the number of degrees of freedom we got now. So we have that many number of coordinates. Okay, small n number of coordinates. These small n number of coordinates are termed as generalized coordinates. Okay, we have small n number of coordinates. All those coordinates are collectively called generalized coordinates. Okay, but keep in mind that usually coordinates, when we specify, we say it as position coordinates. Okay, position coordinates. But keep in mind, in mechanics, these coordinates can be either position, or you can take the variables as energy as a variable, okay, momentum as a variable, or angular momentum as a variable, and in certain situations you can even take charge as a variable. So that's a beauty of these mechanics, in which generalized coordinates can be any variable available in physics. Okay, provided that it gives you necessary result, it gives you truthful, followable, or reliable results, or it explain correct physics. That's the only requirement. Okay, so the remaining number of coordinates are called generalized coordinates, and degrees of freedom we already discussed. And usually these generalized coordinates are represented using a new notation called Q. Okay, usually we express the coordinates using x1, y1, z1, or like that. Okay, but now onwards we will be using this q1, q2, q3 like that. These are the notation used to represent generalized coordinates. Okay, here there are small n number of generalized coordinates. You know, small n signify the degrees of freedom. For example, when you describe pendulum, an oscillating one-dimensional pendulum, q1 will be equal to theta. Understand? q1 will be equal to theta. And when you discuss the motion of an ant on a sphere, you have seen q1 will be equal to theta, and the q2 will be equal to phi. q2 will be equal to phi, because you need two coordinates. So q1 and q2 involved. Again, when you suppose we go for some other planets moving around the Earth or moving around the Sun, you may require perhaps theta, phi, and a radius may be also changing. As you know, really the radius of the planet changes with respect to time. That is not a constant one. So you can have q1 equal to theta, q2 equal to phi, and q3 equal to small r. Understand? So I hope you got an idea about the significance of q's. So depending on the number of variables required, or the degree of freedom, q1 may extend from q1, q2, q3 like that up to qn. Okay, that's the maximum number allowed. Hope this idea is clear. And these generalized coordinates, as I already told you, need not be position. It can be angle, it can be charge, energy, momentum, angular momentum, like that. Okay, many other variables are also possible. So what we do after observing a system and the constraints imposed upon it, one can decide the number of generalized coordinates required to describe the dynamic system. This is a usual procedure. That we will do in many mechanical systems. Okay. Simple pendulum already we discussed how generalized coordinates are fixed, that is mentioned here. Certain coordinates are taken as constraints that can be eliminated, and finally we got 3 minus 2 equal to 1. So number of generalized coordinate required is 1. It is an elaboration of the previous stage. That is all. Okay. And so far we were discussing only about holonomic constraints, and there are non-holonomic constraints too. What is the speciality of what is special with the non-holonomic constraint? In non-holonomic constraints, you cannot express the constraints as with an equality sign. Okay, the constraints which cannot be expressed as a function of the space coordinates or time with an equality sign, that is called non-holonomic constraints. Because one example is given. With this example, let us exaggerate, make it clear. Okay, here there are certain particles moving in a spherical sphere, in a spherical shell. Particles moving randomly within this space. Okay, so the radius of the sphere is, even though it is a constraint, it's a limitation, but they are still free to move anywhere within it. So here we represent constraint as possible distance which the particle can move is always less than or equal to s. Okay, this is a variable. R is a variable, s is a constant. Always particle can move up to s or less than that. Okay, less than that. Here there is a small error. You have to write less than that. R is less than s. Okay. That's more clearly shown here. R is less than or equal to. If you imagine the radius of the sphere is small a, then R will be always less than or equal to. So here a less than sign is coming. It's an equality sign. So any constraint, when we express it mathematically, and if it contains a inequality sign, we call it a non-holonomic constraint. Okay, that is the example shown. Many other examples you can quote, of course. You can take a particle outside the sphere, then you can say this particle's position R is always greater than or equal to radius. Okay, that's also possible. Here less than is taken. Similarly, if the particle is outside the sphere, you can take it as R is greater than or equal to. Maximum it can come up to the surface of the sphere, or beyond it can go to any other value. So other also you can discuss it. So if you discuss in terms of Cartesian coordinate system, you can write it as x square plus y square plus z square, always less than or equal to a square. So when equality sign comes, you cannot solve this equation. It's a problem. Okay, you cannot solve it for z. So z may be either equal to or less than. So the solution is not possible. Or you can also say that you can sometime this constraint can be expressed in terms of differential equation also. Using differential equation. Then for holonomic constraints, such differential equations are solvable or integrable. So all integrable differential equations are holonomic constraints, and all non-integrable differential equations are non-holonomic constraints. So you can say in a non-holonomic case, differential equation may be non-integrable. Then you can count it as a non-holonomic constraint. So both algebraic equations and the differential equation you can write down. One is integrable and other one is non-integrable. Okay, so here comes again another subdivision. Constraints you can also divide into reonomous constraints and scleronomous constraints. What is meant by reonomous? Reonomous means it is in fact a mathematical relation, provided that there is a time variable. If a particular constraint condition expressing mathematically contains time as an explicit parameter, then we call it a reonomous constraint. If the constraint equation contains time as an explicit variable, such constraints are called reonomous constraints. For example, pendulum. If you take the case of pendulum, bob is oscillating, the string is moving, string length is fixed. Usually, in a typical pendulum, string length is fixed. But you can have a pendulum with a string length vary. String length vary. Okay, when the string length is varying, you can say constraint is time dependent. L is time dependent. In that case, we write a pendulum with increasing length or a pendulum with a decreasing length. Also, we can continuously vary the length. That constraint is changing with respect to time. Or suppose you are taking water from a well using a pulley bucket system. Suppose you give some oscillation to the bucket and you gradually raise the water, lift the water from the well, and the bucket is oscillating. Then that is a good example for this Riemann constraint, because length of the rope is decreasing, so constraint vary. Oscillation is still there. Oscillation is bucket is still oscillating. That is another example for Riemann constraint. And here comes scleronomous, scleronomic constraint. Here time is not an explicit factor. That means constraint does not change with respect to time. Very simple example: oscillating pendulum with a constant string is a good example. Okay, or any rigid body system with the interparticle distance constant is an example. But suppose there is a rigid body, not a rigid body. If the interparticular distance are changing, for example, galaxy with all the celestial bodies moving away from each other, where you can disguise it as a Riemann constraint, because in the celestial body distance is changing. So that is an example for Riemann. So time dependent and time independent factor is used to distinguish Riemann and scleronomous constraints. And another thing is about the configuration space. We have a real space with the real coordinates x, y, z. But in a configuration space, we have less number of coordinates, because we reduce the number of coordinates by taking into account the constraint parameters. Okay, just like in a pendulum case, we had a real motion of the pendulum. In a 3D space, we can represent. But when you take it into a configuration space where theta is the only variable, then you can describe its motion using a single variable. So theta will be giving you another sort of curve. Okay. Theta is the only variable. Theta increases, become maximum. Then again it comes down, becomes 0. We get a curve, or we can represent the motion in a single axis. Theta is the only variable. So whereas you represent this motion in a 2D plane, you get a sinusoidal curve. Whereas you represent the motion in a configuration space, you can represent the motion in a single line. That is a difference. Okay. So any space that made with the generalized coordinates are called configuration space, which is required to describe the motion in a simple way. That's the purpose of configuration space. Okay. It is in fact an n-dimensional space formed by these n generalized coordinates of a dynamical system. That system is called, that space is called configuration space. So it has nothing to do with the real space. The real space is there, configuration space is another thing. Okay. Anyway, we will describe more details of configuration space, real space, and phase space in the forthcoming module, definitely. But still, just now we introduced the concept of configuration space. Just understand that it is simply a space made with a number of axes. How many number of axes? That depends on the number of generalized coordinates. So it means that in a configuration space, the axis need not be 3, because in a 3-dimensional space, the maximum possible axis is 3 axes. But in a configuration space, any number of axes can be there. N number of axes can be there. So we can call it even an n-dimensional space. Okay, so and it is a theoretical space. One way you can understand it is theoretical space. Not really you can draw in a paper, or you can make out in a 3D space. and the configuration of a system at any instant is represented with a single point in the configuration space. And as the system evolves, the point also moves. Definitely, because in the system every particle moves, so its position changes. So that can be represented in the configuration space with a single point. Okay, in a single point is you may have n number of particles, but its state or its position or its configuration at any particular time instant can be represented with a single point in the configuration space. That is the beauty of the configuration space, but that is never possible in a three-dimensional space or in a typical real space. I hope you understood the sense or spirit of the configuration space. Anyway, we'll discuss with more example in the next module, the details of configuration space with few more other spaces. Okay, so here now you have an assignment, a simple assignment. Here you can see a rod. It's a rod rotate. A rod is rotating with a constant angular velocity in the xy plane. Rod is rotating in the xy plane with constant angular velocity. And imagine there is a bead on the road. A bead. A bead is there which can move along the road. Bead is there which can move along the road. Bead is taken onto the stick on the road, onto the road, or you can imagine there's a stick or a wire like that. And since bead is moving along the stick to and fro, and the stick is revolving in the xy plane. Hope the system is clear. Mechanical system is clear. You have a stick revolving in the xy plane, and along the stick a bead or a ball, a metal ball is moving to and fro. Okay, this is a system. Now this is the question. Okay, consider a bead moving in the xy plane along a road of length 2r to the origin and is rotating with constant angular velocity omega. Give the position coordinates of the bead at any time instant. Okay, you can give the position coordinates. So there are certain constraints acting on it. Question is oriented about the constraints. Okay, so you have to find the value of x, you have to find the value of y, and you can take the total length as 2r. So half length, and actually the road will trace down a circular path. Okay, circular patch. So the bead's motion is sustained within that circular patch. That is also the circular patch, and it is an xy plane. So you have to get the expression for both x and y with respect to the point O. Okay, first thing, find the value of x and y in terms of omega. Then second question, what type of constraint does the bead follow? What type of constraint does the bead follow, or what type of constraint is imposed upon the bead? You can say in both ways. Whether it is a time dependent constraint or a time independent constraint, like that. Okay, so analyze the problem thoroughly and do the question, and you have to upload in the Google Classroom. Okay, I hope you can do it very simply. Here is the next question. Consider a 3 particle system moving in a xy plane with inter-particle distances fixed. Okay, d12, d23, d31, like that. Particles are fixed. Particles positions are distance are fixed, but as a system as a whole is not fixed. Okay, system can move in the xy plane, but not in the z plane. Okay, so I gave you a clue, not in the z plane. So question is, compute the degree of freedom of the system. A very beautiful question. Again, analyze the problem, understand the problem thoroughly, look at the figure carefully. I'm sure that you can do the problem neatly. Do the problem also and upload in the Google Classroom in due time. So I hope the ideas are clear. You enjoyed the session well. Always try to watch the video twice, at least twice, before attempting the problems. Okay, wish you good luck. Thank you all once again. Thank you.